So how can we interact in a good way with a human being, helping them, supporting them, and not harming them, to create systems, so artificial systems, robotic systems, that hopefully one day can behave like our hands. Standard 3D printers can be used. The only thing you need to do is create your mold in these 3D printers, put the silicon into it, and you can create a very low-cost soft robots.
If you're enjoying this podcast, or even though the idea of what we are building, please hit the subscribe button. It might seem small, but it's a little way of saying thank you. You believe in what you're doing. We are building the biggest tech-related community podcast in Africa, brick by brick, voice by voice. So subscribing is like a tiny little donation, but with massive impact. So, in good manners to you, support it for a long run. Thank you.
Okay, perfect. Good day, Professor Kaspar. It's a very good pleasure to have you on this podcast, Josh Podcast. Uh, I and you would like to have a very brief introduction to whoever is watching this podcast. And firstly, can you go ahead to introduce yourself to whoever is watching and probably share us your work, your journey, and yeah.
Yeah. Thanks again for having me. My name is Kaspar Althoefer. I'm currently professor of robotics engineering at Queen Mary University of London. And I've been working in the area of soft robotics and tactile perception for many years. Previously, I was at King's College London for quite a number of years. And I would say definitely more than 2 decades of work in these areas with applications in medical robotics, nuclear sector, manufacturing. These are and construction as well, I should mention. Yeah.
Okay. So, Professor, can you give us a glimpse through, because many of us are basically students, right? I'm a founder and I was once a student. So, can you give us a brief through, a little glimpse about some of the research work as a professor you've been on to recently in the university? Yeah.
Yep. So my main areas are soft robotics and tactile perception. And that is what interests me really a lot. I take inspiration from biology. So we have our hands, and our hands help us to, interact with the environment. And these are fantastic systems, our hands. We can do so many things with them. We can, manipulate the environment. We can, handle things very easily. So I think fantastic stuff happening there. But it's not only the dexterity of our hands that is exciting for me, but also the sensing that is integrated. So tactile sensing, haptic sensing, integrated in our hands, into our fingertips, allowing us to really understand minute differences in the environment when we start touching something. So we can distinguish between texture. We can also very nicely distinguish between the stiffness of different objects. Is something soft? Is something more rigid? Very easily possible for us. So this is really kind of what interests me, my role model, something I'm aspiring to create systems, so artificial systems, robotic systems, that hopefully one day can behave like our hands. And so that's where these two areas come into, soft robotics and also tactile perception. Because on the one hand, I believe that we need to move away from the very traditional approach of using rigid components for our robots. We know those robots from the manufacturing environment. They were extremely successful there, very good in building cars and other systems, electronic engineering, manufacturing of electronic devices. These kind of robots are perfect. But there are many other areas which are, of course, of big interest for robotics, like, for example, interacting with more dynamic, unknown, unstructured environments. And one particular interest is the human. So how can we interact in a good way with a human being? So helping them, supporting them, and not harming them. So if we look at those rigid robots, then there is a danger that we um, harm the human, that it's not as safe as we would like to have it. So here I think soft robotics has an extremely good possibility to make a difference. So yeah, soft robots to interact with humans, with fragile objects, very important. Yeah,
Yeah,
but
yeah, that was
just to add, the second point is the tactile perception. Um, we have done already quite a lot in soft robotics and achieving good systems, but we want to go a step further and improve even more this interaction between our robotic systems and the environment. So that's where tactile perception comes in. So integrating tactile and force sensors into these manipulation devices to and then also to interpret the signals that come from there to have a better understanding of this interaction. So simple example, you want to pick up an egg. You cannot squeeze too much because otherwise you break the egg, but you cannot also be too little with your forces that you apply because then it might slip down the egg that you want to pick up. So we need to really understand how much force we have to apply if we want to manipulate particular objects.
yeah. So now, that raised some questions based on the title of this podcast. Today's podcast called "Soft Robotics and Tactical Perception." So my first question is: what materials are typically used to build soft robots?
Yep. So there's a wide range of materials and there are a wide range of approaches across the world. Um, Soft robotics really started maybe 10, 15 years ago, and there was a trend to use uh, other materials. So go away from the more rigid metals that are used in the big robotic systems, and also more rigid plastic has been used. But now there is a focus on silicon rubber. So really something that was traditionally not used in that area. And so I personally started around 2012, so 12, 13 years ago, going into that area. And we developed robotic systems made from silicon rubber. And these systems were used for medical application, for surgical applications. So StiffLop was one of our projects. It's an EU project that started in 2012. And here we created these very small, small diameter robotic systems that could be used for keyhole surgery. And as I said, made of silicon rubber, also equipped with pneumatic chambers. So when actuated, they can bend in different directions. So we could, for example, attach a camera at the tip, and in this way go inside the human body through a small opening and support surgery, for example, minimally invasive surgery. Maybe just uh, one more point.
Okay.
So silicon rubber is definitely a great candidate in the world of soft robotics, but we have also recently started looking into fabric-based robots. So another material which was traditionally not used in the context of robotics. So these structures are effectively inflatable structures made from airtight fabric, and again can be used to go into remote areas. So one area is the medical surgical field, but we can also think about construction and the nuclear sector where there are many areas that cannot be reached by humans. And here we have now robots that can extend into these spaces to inspect these spaces or even carry out certain tasks that are relevant for the particular industry.
Thank you very much for that wonderful answers. I find it very fascinating because most times I do see some of these materials used for soft robotics for surgery. Especially, there's one latest news caught up in Japan, a successful surgery done. I think that was some couple of months this year. So, and based on my own knowledge, robots is a very hard object, right? So using, and many people find it that how is can it be even be trusted? Can we trust robots to even perform operations on the human body? Probably, prevention. There are some who are into robotics, but they felt like, oh, maybe, uh, is maybe robots used for this surgery are just made of metals, hard objects, not like you said, soft robotics. So silicon, one of those materials. Is it? I think you mentioned one material, right? Are there other list of materials, but maybe silicon is one of the best materials out there. I don't know.
There are a range of materials and a range of approaches. So silicon rubber is one of them, but there are also let's say materials that are flexible, so not completely soft, but tending towards that idea of creating more soft robotic systems.
Yeah.
And also I should add in addition, there is another cohort of researchers who have a very different approach to soft robotics. So even though they use um, materials that are rigid in the construction of their robots, these robots are programmed to behave like soft robots. So when they contact with the environment, they react to it and reduce the forces they apply to it. So that is they also speak about soft robotics, even though the systems are made of rigid components. So there are a
So,
number of different approaches taken here.
all right. How does a pneumatic actuators work in soft robotics?
Say again. What's
How
your
how, how does a pneumatic
oh yeah
uh,
yeah
actuator work? Yeah.
yeah. So one very common approach is to create these structures, and we can imagine cylindrical structures that maybe have the size of my finger. Sometimes they are larger. Some researchers have also looked into structures that are even smaller than that. And so they are made from the silicon rubber and they are equipped with chambers inside. And these chambers can be then actuated. So you blow air into them, and that will deform then the silicon structure. And then depending on how you organize your chambers within that structure, you can achieve bending in different direction. So that is the kind of fundamental principle behind it. And so you could have multiple chambers in one of those segments, and each segment can then move into different directions. And I'm talking now about these different segments. If you then add multiple segments together, you can also achieve more complex shapes for each segment being able to bend in different directions. So like an S-shaped kind of configuration, and even more complex configurations, which would allow you then to go around obstacles, for example, doing keyhole surgery, going around organs, bring the camera to places that was not possible with the standard rigid component or code.
Okay. You talk about rigid just now. So what are the key difference? Like, what are the difference between soft actuators and the rigid actuators?
Okay, yep. So when I speak about the soft robots and the ones made from rigid components, then those that are made from rigid components, I'm referring to those from the manufacturing environment. Maybe that is the easiest way to imagine it. I suppose most of the listeners know about robots in the car manufacturing sector, which are used to put cars together. So these are hard robots, rigid component robots, and they are made up of multiple links, and they have joints that connect a whole robot together. And usually um, uh, standard DC motors are being used. So these DC motors, direct current motors, or stepper motors, are sitting in the joints and drive those links. And they are electrically powered. So that is a very standard approach. And so we have now moved away, and other researchers, of course, as well, have moved away from that and have now created these robots that don't have these traditional joints anymore. Effectively, our links are now bendable. So our links are not just straight links as we know it from the standard standard robots, but they can bend. So inside these soft links, soft segments, we have those pneumatic chambers that can be moved, that allow us to move the segments in different directions. That is the major difference. I should add, there are also approaches where tendons are being used. So you have a soft structure, and you have tendons or cables attached to these soft structures, and then you have a remote actuator that could be a DC motor that pulls then these tendons pulls them, and that makes the robot move in different directions.
Okay, so now let's dive into the soft robotics now. How are 3D printing used to create soft robotics components?
Yeah.
Can you just give us a brief through about that?
Yeah. This is definitely a very important area, and this is developing. And some researchers use this kind of approach to create soft robotic structures. So effectively, um, the approach becomes then very easy. As a designer of a robotic structure, you sit down, use your CAD software, and develop in there a design for the structure, the robot that you want to create, and then you send it to the 3D printer, and it's done. However, big issue is that these printers are very costly. And I'm talking like £200,000 if you really want to have a high quality printout at the very end. And even if you use a printer like that, the results are maybe not as exactly as you want them, because in a 3D printer, you effectively put the structure together from individual little dots, of material. And if they are not sticking together perfectly well, then you have ruptures, and especially if you then pneumatically actuate them, these structures might become, might have leaks, so they're not airtight anymore. So lots of issues there. So we have chosen a different approach there. We use a 3D printer, but we use the 3D printer to print a mold. And then into this mold, we pour the silicon rubber, which can cure then and creates a structure that is much more reliable, airtight for longer periods, can withstand higher pressures. So it's from our perspective, a much better approach. Also, I would like to add that much cheaper, because standard 3D printers can be used, and they are now at very low prices available, very affordable. And then the only thing you need to do is create your mold in these 3D printers, put the silicon into it, and you can create a very low cost soft robots.
Okay, so can you dive us through some of the ways, some of the simple ways to control soft robotic movements, like soft robot movement? Yeah.
Yep. So it I mean, I will focus on the pneumatically actuated soft robots. There are other approaches, but let's have a look at that. So we create a structure which has is made from silicon rubber, has the air chambers inside, and so the only task now is to effectively, um, pump air into these chambers to make them bend. And um, that is now, and then the control comes into it. So now you need a compressor. So you need a way to compress your air, so that you can pump it into these air chambers. You should have then valves. So these valves are pneumatic valves, which effectively can be controlled so that you can decide how much air goes into your chambers, at any time. And then this valve needs to be connected to a microcontroller. Maybe you have heard of the Arduino microcontroller, and so that can be then programmed to achieve the movements that you want.
Okay. Can they also use Raspberry Pi?
Of course, anything. Yeah, that is no problem at all. So
Because Arduino Pi is for mostly maybe, I mean, Arduino has good capacity, right? But I feel Raspberry Pi does heavy load work to be used for soft robotics, because mostly soft robotics are mostly used in industries, in the hospital, so they need high capacity controllers, like
oh, yeah. It's totally okay to use a Raspberry Pi.
right.
We use Arduino quite a bit in our research.
Okay.
Is often suitable for the things we want to do, but of course, if you want to go a bit further, um, I mean, one big issue is sensing, and we might talk about this a bit more later. But one approach could be to use an external camera to understand the movements of your robot and use this as a feedback for your controller. And then the Raspberry Pi might be the better option because you may need to do some vision processing.
All right. So how do you design a basic soft robotic gripper?
A gripper.
Yeah.
Yep. It it's a design task, mainly. So the emphasis is really on making decisions on what kind of objects you want to grasp, whether it's more small-sized objects or larger objects, and then based on that to design your gripper. So we have designed different types of grippers. Most of our soft grippers are made of multiple fingers, so 4 to 5 fingers. And design-wise, I would suggest, that was our approach, to focus on the individual finger and then think about how you can combine those together to form a whole hand or grasping device.
All right. So what role do elastomers play in soft robotics?
Okay. Yeah. So these are silicon rubber. So you can purchase this from different companies. So EcoFlex is, for example, one type of silicon rubber that you can use, and another one is Dragon Skin. Yeah. My suggestion would be to maybe read the relevant literature and then see what material is best for for the work you plan to do. And maybe, yeah, there's literature out there, and there's a paper that came out a few years back, which gives a fantastic overview of different materials which are commonly used and what are the pros and cons. But one thing I should add, so I can see a lot of potential there using um, those soft materials. However, payload is an issue. So if you want to now achieve high payload, then you may need to think about, see how you can differentiate your approach there. One way forward could be to use fabrics that are used for inflatable structures, create grippers from fabric on a sewing machine, make it airtight, and you can achieve much higher pressures, much higher forces, and that allows you to pick up higher, heavier objects.
Okay. Thank you so much for the explanation. So, there's a question I have right now. I think you've explained it earlier. It was about vacuum-based actuation, right? So, can you basically give us a little brief of how vacuum-based actuation works in soft robots? Just short brief. I know you've discussed that earlier, right? Yeah.
Yeah. In my research, I only work on positive pressure actuation. So we are pumping air into it, and if I gave the impression of having spoken about vacuum-based actuation, then I have to apologize. That is not my area. But I do know.
Well, you can
I
talk
do.
about the one. You can talk about the one you know. Yeah.
Yeah, I do know that colleagues are working in that area. There's, for example, Jimmy Peek, who is in Lausanne at EPFL, and they are applying that to some of their structures. And effectively, what you do there is you design your structure in a way that when you apply a vacuum, you effectively achieve a shrinking in your structure, and that, if the design is right, leads to a bending of the structure. And in this way, you can achieve the bending of fingers, and applying this principle, you can develop grippers.
Okay.
Yeah. I mean, one point to maybe add there is one disadvantage of using a vacuum approach is that it's relying on the difference between the ambient atmosphere, so standard pressure around us, which is 1 bar. So even if you create a fantastic, a perfect vacuum, you can always only create a pressure difference of 1 bar, which is a bit limiting, because on the hand, if you use a positive pressure approach, you can bring up the pressure to higher bars.
Okay. Okay, that's insightful. All right. So what are some of the safety advantages of soft robots in human interaction?
Yep, very clear safety advantages, because our structures, they are just made from soft materials, so they're inherently safe. I appreciate there can be issues if, for example, you apply too high a pressure that something bursts, and that could be also harmful to the body. But principally, we have here devices that are pretty safe, even if
Okay.
the electronics behind it fail. While on the other hand, if you look at the, let's say a rigid component exoskeleton, or a collaborative robot collaborating with a human in a manufacturing environment, for example, then you can program them to behave in a soft way. You can make sure that they, react appropriately, never apply too high forces to the human.
All
However,
right.
if now the electronics fail, if the program fails, if there are issues of that nature, then unpredictable movements could happen in this robotic device, and that could be theoretically harmful. And that cannot happen in a soft robotic device, because it would remain soft.
Okay. All right. Um, Thank you so much, Professor Kaspar. I really appreciate this section with you.